All right, everyone. Let's talk about the rest of the chapter 8 and 9 for the beam analysis and design. So let me share the screen. Okay, so let's talk about the moment gradient. As you know, you remember that we studied in structure analysis that depending on the loadings and loading conditions and boundary conditions, we may have a different variation of bending moment. And usually we are focusing on the maximum value because that is the most critical point in the critical demand. But depending on the distribution of that moment along the length of the beam would affect to the selection of the beam. So here you can see three different cases which will have the same maximum moment demand. So here we have two end moments, m naught, one in the clockwise, the other one is a counterclockwise, so that we have a consistent level of m naught, the maximum moment, all along the length of the beam. This is another case, the same magnitude of the moments, but one in the clockwise, the other one is also in the clockwise. And when we develop the bending moment diagram, we have a positive jump here, and then along the length of the beam, we have a decrease of the bending moment from the m naught going through 0 and going down to negative m naught. So in terms of the maximum moment, it is still m naught, but most of the beam is not under that magnitude, while this one, entire length of the beam is under the same moment, m naught. So we have to have some kind of difference between these two cases at least. And this is kind of in between. So we have the maximum moment at one end. There's no other moments applied. So bending moment diagram, we have a positive jump up to m naught, decrease back to 0. Again, most of the beam is not under the maximum moment m naught. Only this near the edge and the support area is the point where we are expecting to have that level of the moment. So extreme case is uniform moment loading, which is the first one, and variation is the moment gradient, and this is not the loading. This is not the loading. This is coming from the moment, right? So how can we address this into our selection of our beam? And that's the answer to that question is through the C sub B. So remember C sub B, we had two equations for nominal moment, one for inelastic lateral torsional buckling, the other one is for elastic lateral torsional buckling. So go back to this chart. So this equation is for inelastic the lateral torsional buckling. This is for elastic lateral torsional buckling. The equation for the elastic lateral torsional buckling was simplified as FCR times SX. SX is here. Everything except C sub B and SX is called FCR here. So C sub B times F sub CR times SX looks kind of simple equation, but this is equivalent to this, okay? And I said we're not going to talk about this in this class. And even in the inelastic lateral torsional buckling region, we still have the C sub B factor. So what is C sub B? C sub B is a lateral torsional buckling modification factor depending on the moment gradient distribution of the bending moment along the beam. C sub B accounts for the non-uniform moment over the member length. So the most conservative case is uniform moment, which is corresponding C sub V value is equal to 1.0. So C sub B is equal to 1 is the conservative case, which is the maximum case, but you may be able to justify a lighter member. So this is the equation format of C sub B. So how can we find out the C sub B? It is depending on the bending moments at a certain point along the beam from the bending moment diagram. So 12.5 times the maximum moment, and then in the denominator, we have M max and MA, B, and C. So MA, B, and C's are the moment at a certain location, the moment at the quarter point of segment, half point of segment, and 3/4 point of segment. So we're going to break it into 4 segments, and we take the the moment values at 3 corresponding locations, and those are going to be included in this equation. And M max is, of course, is the maximum value from the bending moment diagram. And R sub M value is equal to 1.0 for doubly symmetric members. But we're not using this equation. If you want, you can use it for different cases, but typical ones are coming from this table. So this table is coming from your steel manual, steel Bible, and it covers the most of the typical cases based on the simply supported beam, and which is the usual case, right? So what if we have a simply supported beam and one concentrated load in the middle? Then here we have a corresponding C sub B value, but here we have 2 different cases. One, we do not have any other the lateral bracing. So this is the loading condition. The second column says the lateral bracing along the span. So whether there's no bracing, which means the unbraced length of this beam is going to be the entire length, the physical length of the beam. If that's the case, corresponding C sub B value is going to be 1.32. What if we have one lateral bracing right in the middle, which is the location where we apply the load? Then the corresponding C sub B values are going to be 1.67. So that's how we can read this table. So let's see. Here we have a uniformly distributed load and the intensity is W. What if we have 0 lateral support? Then the C sub B value is going to be 1.14. What if we have 1 lateral support, the bracing in the middle, then 1.3, and so on. So this is how we can read the table, and we're going to use this table and the values from this table, not from the equation. So this chart shows us the influence of C sub B. So earlier when I derived the equation, I initially kind of ignored the C sub B value, and that is this dotted line. But when we include the C sub B value, that will kind of increase the nominal moment, which is good for us, right? Because this M sub N is our capacity, and we are having larger capacity with a given section, which is good, right? So when we apply the C sub B, then we can increase a little bit of our capacity like this, okay? All right, so I'm gonna stop this video clip, which is pretty short this time, and then I'm gonna continue to talk about and solve the example problems from the textbook. All right, see you later.